Keeper 4.7, Taylor polynomials and error bound. Alright, so first thing I want you to do is recall your Taylor polynomial. Just remember how it's set up. Remember you have your derivative over that number factorial times x minus the center to whatever power you're on. Alright, so example 1, it says find the Taylor polynomial of degree 4 of f of x equals e to the 2x centered at 3. So to find this, again, I'm going to start by writing out my first 4 derivatives. And again, I'm using 4 because they want a degree of 4. And so I have e to the 2x, but at 3 is e to the 6. F prime of the function at 3 is 2e to the 6. F double prime of 3 is 4e to the 6. F triple prime of 3 is 8e to the 6. And then the fourth derivative at 3 is 16e to the 6. And so now I'm going to write out my Taylor polynomial. So t sub 4 of x is going to be e to the 6 times 2e to the 6 x minus 3 times 4e to the 6 x minus 3 squared over 2 factorial, which reduces to 2e to the 6. And then I'm going to do my third derivative over 3 factorial, which will give me 4/3 e to the 6 x minus 3 to the third. And then my fourth derivative over 4 factorial is going to give me 4 over 3 e to the 6 times x minus 3 to the 4th. Notice that my final answer, I've already reduced out my factorials. Alright, so part B says, well, use what we just found, use that polynomial t sub 4 to approximate 3.31. Alright, then we're going to find the actual value of 3.31 to determine the error. Remember, error is just the absolute value of the true function minus the approximation. So the first thing I'm going to do is I'm going to find t sub 4 3.31. Remember, our t sub 4 from the previous part A, is given. So t sub 4 3.31 is going to be e to the 6 plus 2 times e to the 6 times 3.3, or 0.31 when I subtract, and so on. So basically, again, I'm putting in 3.31 for all of my x's. And then when I evaluate that using a calculator, I get 749.602 as my approximation. Now, they asked us to go ahead and find the true value of f at 3.31. So remember, f was e to the 2x, so I'm going to do e to the 2 times 3.31, and I get 749.945. Right here, I can already see that my approximation and my true function is very, very close, depending on what we're using this for. I mean, obviously, if we're using it just for a simple math example, it's really close. If you're using it for like some type of medical drug or something like that, for dosing or something like that, that might be really far away. So again, your error is all relative to what you're finding error for. And so to find out the error using t sub 4, I know the error is going to be the true function minus the approximation, the absolute value of that. And so that's going to be the 749.945 minus 749.602. And so my error is 0.343. Now, if you want to reduce your error, you want to go out to a bigger Taylor polynomial, like you would want to use t sub 10 or t sub 100. That will reduce your error. Alright, so in example 1, that was kind of unrealistic because if I used the calculator to find the approximation, I could have used the calculator just to find the function at 3.31. The difference in this example, example 2, is that they don't give us the function. They just give us some terms or some derivatives of the function. So with that being said, I have to use an approximation since I don't know what the function is. And so the first thing I'm going to do is I'm going to write out a Taylor polynomial of degree 3 centered at x equals 5. And since they gave us g of 5 and g prime of 5 and g double prime of 5 and g triple prime of 5, I can write out my Taylor polynomial without having to do any additional work. So my Taylor polynomial of degree 3, so t sub 3, would be 3 minus 2 times x minus 5 plus 7 times x minus 5 squared over 2 factorial over 2, then minus 3 x minus 5 cubed over 3 factorial, which reduces to x minus 5 cubed over 2. Alright, so now I'm going to use that Taylor polynomial to approximate 4.9. So g of 4.9 approximately equals t sub 3 of 4.9. And t sub 3 of 4.9 is going to give me, when I plug it into my calculator, 3.236. All right, so what we are looking at, or what we've been looking at, is using these Taylor polynomials to approximate values. And so next we have what we call the Lagrange error bound. And the Lagrange error bound basically tells you how far off your approximation is going to be. Like, what is the maximum amount of difference between your true function and your approximation. And so basically this Lagrange error bound says if you take k, which k is the largest next derivative, and divided by the next n factorial times your x minus your center over n plus 1, that will tell you how far off your approximation is at most. All right, so example 3, it says let f be the function with 5 derivatives on the interval of 2 to 3. Assume that the absolute value of the fifth derivative is less than 0.2. So that means the maximum fifth derivative is less than 0.2 for all x in the interval of 2 to 3. And that a fourth degree Taylor polynomial for f at c equals 2 is used to estimate f of 3. So first of all, they want to know how accurate is this approximation. Well, our accuracy, again, what we're going to do is set up our error. So I know that my error is going to be the true f of 3 minus the approximation, which would be t sub 4 of 3, since they asked us to use a fourth degree Taylor polynomial. Now, our error is always going to be less than or equal to, using the Lagrange error bound, the maximum of the next derivative. So since we're on a fourth degree polynomial, everything I'm referring to is actually 5. Because 5 comes next after 4. So I wanted to know the maximum of the fifth derivative, which they told us was 0.2, over 4 plus 1, or 5 factorial, and then times 3, because that's what we're estimating, so 3 minus my center, to the 4 plus 1, or 5. And then when I simplify that out, I get that my error has to be less than or equal to 0.00167. All right, so part B says, suppose that t sub 4 of 3 equals 1.763. Use your answer from part A to find an interval that f of 3 must reside. So if we know t sub 4 of 3, and we know that it's going to differ by basically like a margin of error of 0.00167, all I have to do is add and subtract 0.00167 to whatever I get for t sub 4 to figure out my boundary that f of 3 must fall inside. So I'm going to do 1.763 plus or minus 0.00167, and I get, when I subtract, I get 1.761, and then when I add, I get 1.765. So that means f of 3, the true value, the true f of 3, must fall somewhere between 1.761 and 1.765. This is very similar to those of y'all that have taken statistics. This is very similar to like your confidence intervals. All right, so continuing with example 3, it says, could f of 3 equal 1.778? Explain your reasoning. Well, it can't, because we already figured out that our interval is from 1.761 to 1.765. 1.778 does not fall in that interval, and so it can't be a logical choice for f of 3. And then it says, can f of 3 in part D, can f of 3 be 1.764? Well, sure, because 1.764 does fall in the interval of 1.761 to 1.765. All right, so our last example, they're giving us the function f of x equals sine x. First, they want us to find a fifth degree Maclaurin polynomial, so centered at 0 of sine x. Now, again, this should be already something that you guys know. So our t sub 5 of x should be x minus x cubed over 3 factorial plus x to the fifth over 5 factorial. Notice again, they're not asking for 5 terms. They're asking you to go to the fifth degree, so I'm only going to have 3 terms. All right, so the next part says use this polynomial to approximate sine of 1. And so sine of 1 would be t sub 5 of 1, and I plug in 1, I get 1 minus the 6 plus 1 over 120, which approximately equals 0.84167. Now use Lagrange error found to find the maximum error of your approximation. And so the error is going to be the difference between the true and the approximate value is less than or equal to the maximum of the next derivative. So I'm looking for the maximum of the sixth derivative. Well, since our function is f of x, our sixth derivative is either going to be sine or cosine. Like, I really don't care which one it is. And the maximum value that either sine or cosine can go to is 1. So I'm going to use 1 as my k over 5 plus 1 factorial. Again, 5 because we were on the fifth term, plus 1 because I need to go to the sixth term. Times 1, which is what we were approximating, technically 1 minus 0 since that's the center, to the 5 plus 1. When I work that out, I get that my error has to be less than or equal to 1 over 720. All right, so again, that is my maximum error.